come to the next thing. Okay, when I apply, okay, even if it is a non-polar atom, that means let me suppose, okay, this dielectric is made up of atoms. Atoms are neutral, as you have already, as we have already discussed. When I place this atomic substance in between, okay, then okay, this is a neutral dielectric material. When I place this neutral dielectric material in the electric field, okay, when I apply the neutral dielectric material in the applied field, then it gets polarized. It gets polarized. Now, this is what you call it as polarization. It got polarized, and we call it as, okay, this process as polarization. Okay, because of this polarization, okay, there are some induced charges. That means the charges which were not there earlier got generated. Okay, so we got induced charges, okay, negative charges as well as positive charges. Okay, so that implies this neutral dielectric material, when it is placed in an external electric field, it got polarized. When it is got polarized, okay, we got okay, negative and positive charges separated, and we have negative and positive charges separated implies, okay, there will be some electric field, okay, starting from positive charge and moving towards the negative charge. So these red lines are the induced electric field lines. These red lines are okay, induced electric field lines. Now these are the, okay, these are the charges that you applied on the plates. Okay, so this is the applied electric field. Now, because of the applied electric field, there are some charges that are induced, and because of these charges, there is some induced electric field. And the beauty is that the induced electric field is opposite to the applied electric field. That
Applied.
means to say, yeah, that means to say the induced electric field opposes the applied electric field, because of which the net electric field inside the material gets decreased. Net electric field inside the material gets decreased. But outside, there will be electric field which is equivalent to the electric field that you see over here. But inside the dielectric, the net electric field will be the applied electric field minus the induced electric field, minus the induced electric field. Okay, now the same thing is being said in terms of charge densities. Okay, Q is the applied charge, Q dash is the induced charge. Okay, and this Q is placed in on an area A, so Q by A is applied free, okay, charge density rho, and Q dash is placed in on another area A, okay, then applied charge density is rho dash. That is, rho dash is equal to Q dash by
Q
A.
dash
Rho
by
dash is
A.
equal to Q dash by A. Okay, so the net, okay, net charge, okay, is okay, charge density. Net charge density is applied charge density minus induced charge density. So what's happening? By placing a dielectric in between the charged plates, the net charge seems to have decreased. Net charge seems to have decreased, because of which, okay, because of which this can add, or this can take some more charges for a given potential. It can take, some more charges. That's why we say that when I place a dielectric between the charged plates, the net charge storing capacity increases. Net charge storing capacity increases. Okay. Now anyway, from Gauss law, okay, D is equal to Q by A, or you can even say that rho is equal to rho. Okay, I mean this okay, D by epsilon naught, or to say rho by epsilon naught. Okay, Gauss law says that electric field, okay, coming out from a surface, okay, is given by rho by epsilon naught. Okay, now from this we have displacement vector capital D is equal to epsilon naught E. Okay, now making use of these two things, and another definition that okay, rho dash is equal to Q dash by A, and I call this Q dash by A as polarization vector. I call this as polarization vector. Okay, now this is also called as okay, given as, or you can say this is also given as okay, okay, dipole moment density vector. Okay, This is also called the dipole moment density vector. I don't know whether you understood or not. Okay, that means the total dipole moment per unit volume. Total dipole moment per unit volume. So P bar is also called total dipole moment per unit volume, or it can be called as induced charge density vector. Induced. Okay, this Q dash is induced charge by A area. Okay, induced charge density vector. Okay. Now from this, from this figure, what do you see is, net charge, or say net charge density is equal to applied charge density minus induced charge density. What am I doing? I'm dividing both sides with epsilon naught A. Okay, I'm doing dividing both sides with epsilon naught A. So this is what is the expression I have. Now, okay, what I have defined is, okay, this, okay. Mm. This is rho by epsilon naught. Okay, this is rho by, okay, epsilon naught. You don't have a there. Okay, I'm sorry for that. A is already given, Kadama. A is already taken. Okay, rho by A is already taken. Okay, I'm dividing both sides with epsilon naught. Okay, when I divide with epsilon naught, what I have is rho by epsilon naught is En. Okay, what is En? Net electric field inside the dielectric. Net electric field inside the dielectric. Okay, and what is rho? Rho is nothing but your capital D displacement vector, capital D. Okay, and by epsilon. And what is rho dash? Rho dash is nothing but your polarization vector, capital P, so P, and by epsilon naught. Okay, with these two things, what I have is I take epsilon naught to the other side. When I take epsilon naught to the other side, I have epsilon naught En is equal to D minus P, or D is equal to epsilon naught E plus P. Note, D is a displacement vector. E is, okay, I changed En to E. Okay, why? Because in most of the textbooks, you will see this relation like this. That is, D is equal to epsilon naught E plus P. Okay, D is equal to epsilon naught E plus P. But basically, you should understand that the E that is generally represented over here is nothing but the net electric field inside the dielectric. Net electric field inside the dielectric, and not the applied. Okay, not the applied electric field. Okay, so this is how you got a DEP relation. Okay, and generally, okay, it is asked for 3 marks in the examination to prove, to get a relation between D, E and P. Okay, that is displacement vector, electric field vector, and the polarization vector. Okay, for your homework, okay, I want you people to, okay, tell me how P bar is, okay, dipole moment density vector, or, okay, total dipole moment per unit volume. How is P equivalent to total dipole moment per unit volume? Okay, I want you to go home and try to work it out. If you don't work out, to ask any question to me, and you can't ask any question to me, you may not understand. Okay, so I would like you people to go home and work out. Not getting
So,
an answer is not at all a
so
problem.
shall
Not
I?
getting an answer is, yeah. Chapama?
The dipole moment is charge into distance between them.
Yes, good,
So
good.
dipole moment density will be dipole
Ah,
moment by volume.
ah,
So Q will, I mean, charge into the distance by
mm.
volume. Volume means area
Excellent, excellent,
into
excellent, excellent, excellent. Who is that?
region.
Srija, very good, ma. Srija, excellent work. Okay. Now, do okay. I'm not talking anything now. Okay, because Srija has already explained. I mean, answered my question without having to go home and work out. Okay, that's very good, Srija. Okay, your homework is done. I'm happy. Okay, I'm happy that I have very very good students. Okay, who answer my questions immediately. Rather, okay, I must be asking very simple questions in that case. Okay, no problem. I'm happy. Okay, so that's what you have to do. Okay, and next. Okay, these are the different sites from which I have taken many of them. Okay, and okay, many of them have given